So, in today's class I will be discussing some more solutions of second order differential equations. I will be talking mostly about homogeneous equations and a very little bit about non-homogeneous equations. So, let us just remind ourselves what we know about second order differential equations. So, we said that we can write as a general second order differential equation, second order linear differential equation as in this form: a of x y prime plus b of x y is equal to c of x. This is if c of x is not equal to 0, this is called non-homogeneous. C of x not equal to 0. If you have c of x equal to 0, then you have something like this: y double prime plus a of x y prime plus b of x y equal to 0. This is homogeneous, and we saw that for homogeneous equations you have basis functions. Okay, so you can write you can write your general solution as a linear combination of basis functions c1 y1 plus c2 y2, where y1 and y2 are solutions of the differential equation. So, homogeneous differential equations have this nice feature. Okay. Now, which is not there for non-homogeneous equations. So, you cannot write this for non-homogeneous equations. Okay. And you can easily verify this for certain non-homogeneous equations. Okay. So, today I want to first start the discussion of a special type of homogeneous linear second order differential equation. It is those with constant coefficients. Okay. So, what do you mean by constant coefficients? So I will say second order linear homogeneous equations with constant coefficients. So, all you will do for constant coefficients is that you will say this a of x and b of x are constants. These are in general functions of x, but if these functions are constants, then you will get a second order homogeneous equation with constant coefficient. So, you will have y double prime plus a times y prime plus b times y equal to 0. A and b are constants. Okay, so a and b are constants, and obviously y is a function of x. Okay. Now, how do you solve such a differential equation? Okay. Now, again there are you can do this using the system of differential equations. You can convert it into two first order differential equations, and then you can use matrix methods. Okay. Alternatively, you can directly do this in using trial solutions. So, you try a solution y equal to e raised to lambda x. Okay. And I didn't put a constant before this, because you can put any constant and it will still be a solution. Okay. So, since it is a homogeneous equation, I can always multiply it by constant and get another solution, but so I will just put y equal to e to the lambda x. I will not bother putting the constant in front. So, if y equal to e to the lambda x, then you know that y prime equal to lambda times e to the lambda x, and y double prime equal to lambda square e to the lambda x. Okay. And now, if you substitute these in the differential equation, okay, then you get what do you get when you substitute this in this. So, y double prime is lambda square e to the lambda x plus a lambda e to the lambda x plus b e to the lambda x equal to 0. And since this is true for all x, I can cancel this e to the lambda x term. I get a relation lambda square plus a lambda plus b equal to 0, and a and b are constants. So, this implies lambda equal to negative a plus minus square root of a square minus 4b divided by 2. Okay, so it is a quadratic equation and these are the solutions. So, what I can write? I can write let us say I call it lambda 1 as minus a plus square root of a square minus 4b divided by 2, and if I write lambda 2 as minus a minus square root of a square minus 4b by 2. Okay. Then I have two solutions. So I have y1 is equal to e to the lambda 1x and y2 equal to e to the lambda 2x. Okay. Now, if lambda 1 and lambda 2 are distinct, okay, then these two solutions are linearly independent. Okay. So if lambda 1 not equal to lambda 2, okay, then solutions are linearly independent. Okay. And if they are linearly independent, then you can write a general solution y is equal to C1 y1 plus C2 y2 is a general solution. Okay. Now, this is very nice because we converted our differential equation into a simple quadratic equation, okay, and we know the roots of the quadratic equation and we can immediately find the solutions. If they are not linearly independent, if lambda 1 is equal to lambda 2, what do? Okay, well it is not too hard, you can find one solution, okay, but you learnt in the last class that once you have one solution, you can find the second solution by variation of parameters. Okay. So the second solution, so if I just have one y1, I can find a linearly independent solution by using method of variation of parameters. So I will just write, so if lambda 1 equal to lambda 2 equal to lambda, okay, then y1 equal to e to the lambda x, okay, and we can find linearly independent y2 by variation of parameters. Okay, what we did in the last class with those u and so on. Okay. So if you go ahead and do this, then what you will get is that you will find that this will lead to y2 is equal to x e to the lambda x. Okay. So the general solution y is equal to C1 e to the lambda x plus C2 x e to the lambda x. Okay, and these two are linearly independent solutions, and that is what you can do, and you can easily verify this. Okay. So I will just say that you can verify this using the methods that we did in the last class. So you write your y2 as u times y1, okay, and then you substitute in the differential equation, and after all this cancellation and everything, you will find that u prime equal to 0, and so u will be equal to constant capital U, and so and after that, since u is a constant, your small u just becomes equal to x. And so I can write y2 as x e to the lambda x. What this shows is that if you have a homogeneous equation with constant coefficients, okay, then you know the solutions, you can always find two linearly independent solutions. Okay. Now let us look at the nature of the solutions. So the solutions, we said that you have lambda is equal to negative a plus minus square root of a square minus 4b divided by 2. So if a square minus 4b is greater than 0, strictly greater than 0, okay, then we have two real roots, okay, two real roots, that means lambda 1 and lambda 2 are real, these are real numbers, okay, then the solution y is equal to C1 e to the lambda 1 x plus C2 e to the lambda 2 x is exponential. Okay, so it's basically a sum of exponential functions. So it involves two exponential functions and it's a sum of these two exponential functions, and you know, lambda 1 can be positive or negative. If it is positive, then it is exponentially increasing. If it is negative, it is exponentially decreasing. Okay. Now if a square minus 4b is less than 0, okay, then two complex roots, I will just call the two roots as lambda 1 equal to lambda real plus I times lambda imaginary. Okay, so lambda I is the imaginary part, which is basically this term, the second part of this solution. Okay, lambda real is basically minus a by 2. Okay, and similarly lambda 2 will be exactly the same, lambda real minus I times lambda imaginary, where I will just emphasize again. So lambda real is equal to minus a by 2 and lambda imaginary is equal to 4b minus a square root of that divided by 2. Okay, so since a square minus 4b is less than 0, so 4b minus a square is greater than 0. So the imaginary part is just this. Okay, and that is multiplied by I. Okay, so the two complex roots have this feature. Okay, so then I can write my y as C1 e to the, now lambda 1 will have a lambda real plus I lambda imaginary. So I will just take the lambda real times x, okay, and then I have e to the I lambda I times x, and in the second case for my second function again I will have C2 e to the lambda r x and e to the minus lambda I x. Okay, so I can write this as e to the lambda r x C1 e to the lambda I times lambda I x plus C2 e to the I times lambda I x. Okay, and again I want to emphasize that both lambda r and lambda I are real quantities. Okay, so this is basically an exponential multiplying an exponential of imaginary number. Okay, and you know that exponential of imaginary number can be written as a linear combination of sines and cosines. So you know that e to the I lambda I x can be written as sine of lambda I x plus I times cosine of lambda I x. Okay, so this is a general property of an imaginary number. Okay, so you can write it as a sum of sines and cosines. So essentially what you have here is these functions look like a combination of sines and cosines. So what you have is an exponential function multiplying an oscillating function. Okay, so you have an exponential function multiplying an oscillating function. So you have an exponential multiplying an oscillatory function. Okay, so this is a case when a square minus 4b is less than 0. Okay, so a square minus 4b is greater than 0, then you have only exponential functions. If you have a square minus 4b less than 0, you have exponential multiplying an oscillatory function. And what about if a square minus 4b equal to 0? A square minus 4b equal to 0. Okay, then the solutions will just be, it will look like e to the lambda x, and you have C1 e to the lambda x plus C2 x e to the lambda x. So, you have only one root, okay. So, both the roots become the same, okay, because lambda equal to lambda 1 equal to lambda 2 equal to minus a by 2, okay. So, the solutions just look like this, okay. So, lambda is just minus a by 2. So, you have e to the minus a by 2 x, okay, and you have C1 plus C2 x. So, the other linearly independent solution is just x e to the lambda x. Okay. Now these ideas that we said here are actually seen in a very practical situation, which is called the damped harmonic oscillator. So, what is the damped harmonic oscillator? So, the damped harmonic oscillator satisfies a differential equation y double prime plus 2 eta y prime plus omega square y equal to 0. Okay. So, if you did not have this middle term, then it would just be a simple harmonic oscillator y double prime plus omega square y equal to 0, but this is a damping term that is there, okay. And I should mention that eta and omega square are both greater than 0, okay. So, now this is exactly of this form that we had before. This is exactly of the form of this second order differential equation with constant coefficient. So, it has exactly this form. Instead of a you have 2 eta and instead of b you have omega square, okay. And the reason we put omega square is because we want this quantity to be strictly greater than 0, okay. Now, there are 3 possible cases. So, case 1 is when what you have is you can say that it is square of this. So, 2 eta square minus 4 omega square is let me say greater than 0, okay. So, in other words, this will, so I can cancel the 4 and what I will get is eta square is greater than omega square or eta is greater than omega. So, you have the case. So, if eta is greater than omega, then this quantity is greater than 0, and what we said, if this quantity is greater than 0, you have exponential solutions, okay. So, the solutions are exponential, okay, and you will recall the solutions look like e to the lambda 1 x and e to the lambda 2 x, where lambda 1 and lambda 2 have this form. I will write it explicitly. So, lambda equal to, so in this case you get minus eta plus square root of eta square minus omega square, okay, and you have, so you have plus minus this, okay, and since eta is greater than omega, okay, then this solution will be purely exponential, okay. So, your solution looks like e to the lambda 1 x plus e to the lambda 2 x, okay. So, this is the first case. Now, notice that if eta is greater than 0 and if eta is greater than omega, then you know that the root where this is plus, okay. So, this quantity will always be less than eta, okay. So, this lambda will always be negative. So, what you have is exponentially decaying solutions. So, I can write this as exponentially decaying solutions. Or you say that the solution is over damped, okay. So, this is called an over damped oscillator, okay. In case 2 you have eta less than omega, okay, and now your solutions are now you have exponential multiplied by this exponential of imaginary. So, exponential multiplied by oscillating, okay. So, these are, so in this case your solutions are actually you have both these oscillations and you have these exponential functions. So, in this case you say that the solution is under damped, okay. And what does this solution look like? So, it will look like it look like e to the minus eta x C1 e to the I omega x plus C2 e to the minus I omega x. You can verify this, just I just wrote exactly what you had in this case, okay, lambda r and lambda I. The third case, lambda equal to omega, is called as critically damped. Okay, and here the solution looks like e to the minus lambda x C1 plus C2 x. Okay. So, basically each of these solutions has a different feature. In the first case you just had exponential functions, in the second case you had exponential multiplied by some oscillating functions. Okay. So, this might look like if you plot this, okay, if you plot y as a function of x, then what you will get is you have an exponential minus x. So, you have this, but then you have oscillation. So, it will look like oscillations whose amplitude is constantly decreasing. Okay. So, this is what happens in the underdamped case. Okay. In the overdamped case you just have, you do not see any oscillations, you just see exponential. So, since they are negative exponential, you will just see something like this. Okay. And critically damped is just at the boundary when you are about to get oscillating solutions. Okay. So, you do not have oscillating solutions, okay, you are just about to get right when you are going from exponential to this exponential multiplied by oscillating solutions. So, these are well known solutions of the damped harmonic oscillator, okay, and we can see them in a very easy way using the solution of the differential equation. Okay. Now, next I will just mention another type of equation which you can also solve using very similar tricks. Okay. So, this equation has a form, so this is called the Euler Kashi equation, and this has a form x square y double prime plus a, which is a constant, times x y prime plus b times y equal to 0. Okay. Now, notice what I did was, when I had a second derivative I multiplied by x square, when I have a first derivative I multiplied by a constant by x. Okay. So, that is what the terms look like. So, if you want you can take the x square in the denominator, but you do not need to do that. Writing it in this form suggests you what the solution should look like. Okay. So, what should the solution look like? Now, you know that when you take a second derivative of some power of x, then you get power of x reduced by 2. Okay. So, now you are squaring, now you are multiplying by x square, so you will get back to the same power of x. Okay. So, the trial solution here y equal to x raised to m. So, if you try a solution of y equal to x raised to m, then you get y prime is equal to m x raised to m minus 1 and y double prime equal to m minus 1 x raised to m minus 2. And now, if you substitute in this equation, so x square times y double prime will give you m minus 1 into x square into x raised to m minus 2. So, all you will get is m minus 1 into x raised to m, okay, and plus a. Now, x times y prime is just m times x raised to, now you had m minus 1 and multiplied by x gives you x raised to m, and b times y is just b times x raised to m equal to 0, and by doing this you can see that you can cancel the x raised to m. So, just as in the last case, you get an equation m minus 1 plus am plus b equal to 0. This is a quadratic equation in m. Okay, and I can write it explicitly as m square plus m times a minus 1 plus b equal to 0. Okay, so that is the explicit quadratic equation in M. Okay, and whenever you have a quadratic equation, you can have two roots. So, two roots M1 and M2. Okay, and again you can have the similar cases. So, M1, M2 can be both real, or it can be both complex. Complex means they have both a real and an imaginary part, and you can have or you can have M1 equal to M2. Okay. So, these are the three cases, and I will not do this explicitly, but you can see in which case you would get each of these. So, you would get both real if this b square minus so a minus 1 square is greater than 4b. Okay. And they will be both complex if a minus 1 square is less than 4b, and you will get two coincident roots if a minus 1 whole square equal to 4b. Okay, so these are the conditions in which you will get these solutions, and you know what to do if you get. So the general solution will look like in the first two cases you can write y is equal to c1 x raised to m1 plus c2 x raised to m2 if m1 is not equal to m2, and if m1 equal to m2, okay, then you find one root and you get the other root by variation of parameters. So if m1 equal to m2 equal to m, okay, then you say y1 equal to x raised to m, okay, and when you solve for y2 using y2 equal to u times x raised to m, u times y1 or u times x raised to m. Okay, so you can make this substitution, you can put in the differential equation and you can solve for y2. Okay, I won't do this. Okay, so but I'll leave it as an exercise for you to try. Okay, so try to solve for y2. Okay, using the same variation of parameters that we had done in the last class. Okay, so I'll stop this discussion on homogeneous second order differential equations here. Okay, so in the next class I'll tell you what to do if you have a non-homogeneous second order differential equation. Okay.